Okay, so we're back and we're going to continue with circular motion, and this time we're going to talk about angular displacement. So in the previous video I explained about angular velocity, angular displacement, and we got it. I wrote the symbol as change in theta or delta theta. So from linear motion, displacement, or you can say distance, same thing. Displacement is having direction and distance doesn't have direction. That's the major difference. So under circular motion, angular displacement is given by this relationship: distance traveled around the circle, sorry about my handwriting, divided by the radius of the circle. So this is the relationship that we shall use to find angular displacement. Now, angular displacement simply describes an change in angle. This change in angle, in the first video, I've made it clear that the angles are always measured in radians because they are always very, very small. Okay, so take an example. If we have a circle with a center and we have this, this is the radius. So the change in the angle is that we can call it delta, or like change in angle, or we can just write theta there. So this part here is the length of the arc, and we normally give it letter S. S is not a unit, it's just a symbol that represents the length of the arc, this part here. Okay, yeah, so basically this is angular speed. So the change in, I'll change the color, the change here is given by this relationship that I've written, and basically that's it. Okay, we shall talk about it more in our next video as we continue. But when the angle is equal to 1 rad, yeah, you can write this as a note. So when the angle is equal to 1 rad, then that means that the length of the arc, okay, you can write it like this: length of the arc will be equal to, is equal to the radius. So when the angle is 1 rad, remember we don't measure it in degrees. When the angle is 1 rad, the arc length will be equal to the radius of the circle. So basically what I'm saying is when this is 1 rad, it simply means that S is equal to R. This is a condition that is true when we are dealing with angular displacement. Okay? Yeah, so let's continue to the next subtopic under circular motion, and that will be angular velocity. Change. I hope this is okay. I'll just move it on the sides, and we go for angular velocity. So angular velocity, first of all, symbol is written like a W, but we call it omega. So whenever I say omega, this is W, and this is given as definition rate of change of angular displacement. Rate of change of angular displacement. Okay, so rate of change of angular displacement, and then it is also measured in rads per second, or it is measured in, this is how we write rads per second or that. Either way it is all correct. Okay, so the formula from the definition, this gives us the formula omega, or angular velocity, sometimes called angular speed, is change in displacement with time, change in time. So rate of change of angular displacement with time. So this here is the formula for angular velocity. Okay, so this one is the angular displacement. Remember the units, we said the unit is radians. I hope I'm loud enough. And the time, the t is time interval, in seconds, or s. The reason I write SEC, some students write an S like a 5, which is kind of confusing. Yeah. Okay. So if we are talking, remember there are two things. Okay, there is angular velocity and there is linear speed. I'll demonstrate that in the diagram here. So if something is moving in a circular behavior or a circular path, if it is at this point, it will be moving like that, and then when it reaches a certain point, it moves like that. So all these arrows are V's. So this is linear speed. Okay, but then the speed along the circular path is what we call angular speed or angular velocity. Do you get the difference? So this is angular speed v, but there is also angular velocity omega. So to get angular speed, to get linear speed v, this is linear speed, and it is represented by v. So v is equal to, I already explained what omega means. So to get linear speed v of the object moving in a circular path, we multiply the angular speed times the radius of the circular path. Okay, so where this v here is the linear speed, this is the angular speed. I want to get the difference, and this is radius of the circular path. Sometimes they call it the orbit, but I prefer calling it circular path. And this is measured in meters. Linear speed is measured in meters per second, and angular speed is also measured in rads per second. Okay, so I hope you get this clearly. Does it make sense? If it doesn't, please feel free to ask anytime during the lesson. So we talked about angular displacement, that is change theta. We said that if the change theta, if the angle that is subtended to the center by the arc of the circular path is 1 rad, then the length of the arc is equal to the radius of the circular path, and then that brings us to angular velocity, which is represented by omega, and omega looks like a W. So omega is rate of change of displacement. So from the definition we get the formula, which is change in angular displacement divided by the time interval, or change in t. And we say there is also what we call linear speed, which is given by this formula here, omega r. Okay, So yeah, so let's continue. So from this formula here, we shall build it. So from here, just trying to summarize. So from this, V is equal to omega R. We can now make omega the subject. It will be V over R. Okay, so V over R. So this is another expression. If we are asked to calculate angular speed and we are given linear speed and radius, we use this relationship. Okay, and this can also be given as, I'll write another version. This version is omega will be 2 pi f. F meaning frequency. Okay, this is frequency. Okay, and then since frequency is 1 over capital T, number of oscillations per second, so we can now write omega as 2 pi over capital T. So this one is also a formula. These three that I'm putting in boxes are different formulae that we can use to calculate angular speed depending on what we have been given. Okay, I'll try to give a quick example here from past paper, of course. Okay, so I'll write the question here. Try to, let me type it. Okay, typing is faster now. I'll write. So a bird flies in a horizontal circle with an angular speed of 5.25 rads per second, of radius 650 meters. Then calculate part A, the linear speed of the bird. Part B, angular frequency of the bird. Okay, sorry, my handwriting is a bit crazy, but I hope you understand. So a bird flies in a horizontal circle with an angular speed of 5.25 rads per sec, and then the horizontal circle has a radius of so basically when we are solving, okay, I'll write on the sides the solution. So we first identify what we have been given. Okay, first of all, we have been given omega as 5.25 rads per second, and we have been given the R as 650 meters. So linear speed V is equal to omega R. So since everything has been given to standard units, we don't need to convert anything. So 5.25 times 650. So the V becomes, from the calculator, it will become 340. But now linear speed is measured in meters per second. So we write that. Okay. 340, but this is rounded to two significant figures, otherwise the answer was, on the calculator the answer is 341 2.5. Yes, I'm also using a calculator here. So you can relieve it like this, or you can write two significant figures or three significant figures. So basically, actually, this needs to be edited. So if this is what we get from a calculator, to write three significant figures, it will be 1, 0. Okay, so these will be three significant figures, and then you can write 3SF there. I hope that makes sense. This is part A. Okay, this is part A. Now for part B, angular frequency. So from omega equals 2 pi f, we bring out the version of omega that has an f in it. So omega is 2 pi f. Okay, now that we know what omega is, they gave it to us is 5.25, and 2 pi. Remember, this pi is not in radians, just the normal pi, so we can do it like that, and then f. So pi is a constant, so we can divide by 2 pi on both sides, and then by the way, you can just say 5.25 over 2 pi, but remember we don't put rads here. This is the normal pi, 3.142. okay, and then we can give it the unit of frequency as hertz. You can even leave your answer like this, it will always be marked correct. So this is part B.